Welcome, geniuses, to the final part of Unit 3. We are going over Objective 3.6. Explain how the definition of an angle as a pair of rays makes the rigid motion-based definition of congruence work for angles that appear to be different lengths. Well, let's start off. I'm going to go level by level, and I'm basically going to start off with, well, what's the definition of an angle? We started off in this top left corner here. The definition of an angle is two rays joined together at a common vertex. They ask you actually two questions. They say, what's the rigid motion definition of congruence? Well, we looked at that in the last unit. Two figures are congruent if one can be overlapped with the other using only rigid motions. And what is the formal definition of an angle is two rays joined together at a common vertex. So what does that look like? It looks like this. That would be two rays. Here's ray 1. Oops. Here is ray number 1 and ray number 2. Those two rays are joined at a common point known as the vertex. So if you're looking for what's a ray, remember, go back to your very first original definitions. What's a ray in geometry? It goes off infinitely in one and only one direction. What's the formal definition of an angle? It's two rays joined together at a common vertex. So you got those two rays, and you see how the space in between them kind of forms an angle. So what's that point called? That point's called the vertex. Why, level 2, is to understand basically what it says right here. Why does the rigid motion definition of congruence require that angles be not made of rays and not line segments? Well, let's take an example where we have two angles. Look at the bottom right corner here. Let's say we've got this angle and this angle, and they're both defined using segments. Now let's say I measure these and they're both 90 degrees. If I measure them and they're both 90 degrees, that means they have to be congruent. They have to be the same number of degrees and therefore congruent. But notice that I can't really rigid motion this one to go on top of this one. Why not? Because they're not the same size in terms of their actual lengths. If one is longer than the other, like how this is longer than this, I can't really rigid motion them to go exactly on top of each other. I can get them to match at least at the corner, but I can't get them to match exactly with the lengths included. So here's my explanation right here. If rays go on infinitely, they can ensure that angles with the same measure overlap with rigid motions. Well, rays go on forever. So if I don't use line segments and I use rays instead, I instead use rays here. Then, when I try to go and overlap this one with this one, when I try to coincide them, they're going to coincide perfectly because they both go on forever. As long as they have the same number of degrees, they're going to be able to rigid motion onto each other because both of them are infinite in size. Both of them continue as far as you'd like them to in both directions. This and this. Might need to do some rotation, might need to do some translation, reflection, whatever it is that you need to do, but you are always going to be able to overlap them as long as you use rays instead of line segments. Whereas line segments, because they have a finite length, they're only a tiny amount of space. They're only this long or only this long. Maybe they're only 5 meters long or 5 inches long, whatever. Then they're not going to be able to overlap with any other angle with the same number of degrees. So that's why the formal definition of an angle includes us having always rays, not line segments, so that it doesn't matter what size we're using. Okay, let's go to the very last one, is create your own definition. So we're trying to think of an alternative but equivalent definition of angle and something that works with the rigid motions. Well, okay, what do we mean by equivalent? I mean, it's going to work the same way. We're still going to have a situation in which if we have the same angles, the same number of degrees, then it's going to be congruent. But it's not the same definition, not exactly the same. I'll give you some ideas on here. I actually would love if you paused it and thought of it. Like, what could I use other than two rays in order to make an angle? But here we go. Here are some of my ideas. I'm not explaining why it is, though I will explain it in the video. So I'm not explaining why it is, at least in this part, in the written part, but I'll tell you why right here. Let's look at number 1, the set of interior points formed by two rays joined at a common vertex. So instead of using the actual rays themselves, right? Instead of using this and this, we take the two rays formed a common vertex and use this space, the set of interior points, as the angle. We now are thinking a little bit more intuitively. Instead of just thinking of the two rays, we're thinking of the space in between the rays. That's what angles are. Angles are the space in between two rays. You take the space inside of it and compare it to the space inside another angle of the same measure. If they're the same amount of degrees, they're going to have the same amount of space inside, and you're going to be able to rigid motion one onto the other. So this is really explaining why it works with the original definition. They are both using the same pair of rays. Or try out number 2. Number 2, right here, I use the example 2 line segments of length 1, both extending from a common endpoint. Well, what does that have to do length 1? Well, I could have picked any number there. 1 just happens to be a particularly nice number to use. But if you have a common endpoint, like this, and you say both of these are, say, 1 centimeter, they're both the same length, then if I try to overlap that with another angle, as long as they're the same number of degrees, which these are not, as long as they're the same number of degrees, I'll be able to coincide one with the other because they're both the same length. So what you've done is called normalizing it. I'll even write that fancy word down for you because you guys are the geniuses. Normalize is to make everything the same length. So now you're not worried about, you're no longer saying like, oh, my angles, one is really big and the other is really small. Now every piece is defined to always be the right length. So we're talking about the 2 line segments of length 1 extending from a common endpoint. And that would form an angle as well. So that's a way to work with it. And we're trying to, this is really hard to explain over video, but ask questions about this, talk to me, and we'll try and get this to a level where everybody can master this. We're overall trying to get through one major point, which is this. Because angles are defined to be congruent using rigid motions, that's the definition of congruent, we need a definition of angle that works with that. And that's why we use rays, because rays are of infinite size, and therefore rays can make it so that we can do whatever size we want. We don't need it to be necessarily one particular size. Then we can just rigid motion one onto the other without any issues. Whereas if we worry about the size, of those line segments, then we're going to have a tough time because we're not going to be able to rigid motion our things to coincide perfectly.